When you look up at the night sky, it feels endless, doesn't it? Every tiny spark out there holds a story older than we can imagine. Somewhere in that quiet sea of light, strange things are moving, stars fading, worlds forming, and invisible forces shaping everything we know. Among them are black holes, places where light itself disappears. But what if there were something opposite, a white hole, shining out instead of drawing in? And what if, somewhere far away, the two were to meet? Tonight, let's drift into that thought together and see where it takes us. If you enjoy these quiet journeys through space, remember to follow along so you don't miss the next one. For a long time, scientists have wondered whether white holes are real or just beautiful ideas written in the language of math. Still, the thought of one meeting a black hole has a way of stirring the imagination. If such opposites were ever to cross paths, it would bring together two of the most powerful forces we know, each following its own strange set of rules. That meeting could change how we think about gravity, time, and even the shape of the universe itself. A black hole is one of space's deepest mysteries. It holds so much mass in such a small space that its pull becomes impossible to resist. Everything that comes too close, even light itself, is caught and can never escape. The edge of that invisible trap is called the event horizon. Once something crosses it, there is no turning back. Yet, at that moment, there's no sign, no shock, nothing that tells you you've gone too far. Physicists say black holes act like perfect black bodies. They don't reflect any light at all. For a while, they seemed like silent creatures of the cosmos. But quantum physics whispered something new. Stephen Hawking showed that black holes aren't completely dark. They give off a faint energy now known as Hawking radiation. It's so weak, so cold, only a tiny fraction above absolute zero, that no telescope today can truly see it. The idea of such dark, heavy stars began long before Einstein. In the 1700s, Jean Michel in England and Pierre-Simon Laplace in France imagined stars so massive that even light could not escape their pull. Michel even guessed that these invisible stars might reveal themselves through their effect on nearby visible ones. Laplace agreed, suggesting that some stars might simply be too large for their light ever to reach us. Their thoughts were ahead of their time. As the 1800s unfolded and scientists learned that light behaves like a wave, they struggled to see how gravity could ever hold it captive. The idea faded, tucked away like a forgotten dream, until the early 1900s, when Albert Einstein reshaped our understanding of gravity itself. His theory of general relativity showed that gravity could bend the path of light, curving space and time around massive objects. Not long after, a German physicist named Karl Schwarzschild solved Einstein's equations and revealed what we now recognize as a black hole. He described a perfect sphere of mass so dense that it created a point of no return, the boundary we call the Schwarzschild radius. Soon after, other thinkers like Johannes Droste, Arthur Eddington, and Georges Lemaitre helped refine these strange new ideas, showing that what once seemed like a physical edge was instead a quirk of mathematics. In the early 1932s, a young physicist from India named Subrahmanyan Chandrasekhar began to look more closely at what happens when a star runs out of fuel. Using Einstein's ideas about relativity, he found that stars heavier than a certain limit could not hold themselves up forever. Beyond that mass, they would keep collapsing without end. Today we call that limit the Chandrasekhar limit, about 1.5 times the mass of our Sunday. Many scientists at the time found it hard to accept, but Chandrasekhar was right. Stars just above that weight become neutron stars, while even heavier ones can fall completely into black holes. By the 1,950 seconds, David Finkelstein described these black holes as true regions of space where nothing, not even light, could escape. For years, many people thought they existed only in theory, like ideas drawn in chalk on a board. But in the 1,960 seconds, that changed. Astronomers began to see that Einstein's equations really did predict such objects in nature. The first one to be identified was called Cygnus X1, found in 1971. Since then, more have been discovered, some small, others unimaginably large. Black holes are born when massive stars reach the end of their lives and collapse under their own weight. Once formed, they can grow by swallowing nearby gas or even merging with other black holes. The largest of them, called supermassive black holes, hold millions of times the mass of our Sunday. Almost every galaxy has one resting at its center. Ours does too, a giant called Sagittarius A*, with the weight of about 4 million suns. Astronomers cannot see black holes directly. Instead, they watch how matter behaves nearby. Gas and dust swirl around them, heating up as they fall inward, glowing with light so bright that it can outshine a whole galaxy. When this happens, we see what's called a quasar, a brilliant beacon from far away. Even stars that wander too close can be torn apart, leaving behind a final burst of light before disappearing. Sometimes, the invisible tug on nearby stars gives away the black hole hiding in the dark. Back in 1939, Robert Oppenheimer and George Volkoff built on Chandrasekhar's ideas to show that even neutron stars have their limits. Above a certain mass, they too would collapse into black holes. This threshold, known as the Tolman-Oppenheimer-Volkoff limit, was first thought to be less than the mass of our sun, but later studies placed it between 1.5 and 3 times that amount. Decades later, when scientists watched 2 neutron stars collide in 2017, a bright event called GW170817, they saw signs that a black hole had formed, helping them refine the limit to just over twice the mass of the Sunday. Oppenheimer also wondered what time would look like near the edge of a collapsing star. To someone watching from far away, the star's surface would seem frozen in time right at the boundary known as the Schwarzschild radius. To someone falling in, though, time would keep flowing as usual. Because of this strange difference, he called them frozen stars. That same year, Albert Einstein tried to show that black holes could not exist at all, though his own equations told another story. Just months later, Oppenheimer and his student Hartland Snyder used those very equations to prove that black holes could indeed form when stars collapsed. It was the first clear picture of how such an object could truly exist. In 1958, David Finkelstein gave new meaning to the Schwarzschild surface. He called it the event horizon, the point of no return. Around that time, Martin Kruskal and others developed new ways to describe space and time near this boundary, giving scientists tools to understand what an observer might see while falling into a black hole. By the mid-1960 seconds, black holes were no longer just curiosities. They had become one of the central puzzles of modern physics. In 1963, Roy Kerr found the solution for a spinning black hole, and 2 years later, Ezra Newman extended it to include electric charge. Soon after, other physicists, Werner Israel, Brandon Carter, and David Robinson, showed that a quiet, stable black hole could be described by just three things: its mass, its spin, and its charge. People began to call this the no-hair theorem, meaning that black holes are simple at heart, no matter how wild their beginnings. At first, many thought the strange singularities inside black holes were only math errors. But in the late 1960 seconds, Roger Penrose and Stephen Hawking proved that these points of infinite density were real features of collapsing stars. It was a turning point in our understanding of gravity. Penrose later received the Nobel Prize for this work, and Hawking became one of the most beloved voices in modern science. As theory advanced, so did observation. In 1967, Jocelyn Bell Burnell and Anthony Hewish discovered pulsars, steady pulses of radio waves from space. These turned out to be fast-spinning neutron stars, proof that such dense objects truly exist. In the early 1970 seconds, new data confirmed that Cygnus X1 was a black hole, the first that most scientists agreed was real. Around the same time, James Bardeen, Jacob Bekenstein, Brandon Carter, and Stephen Hawking began connecting black holes to the familiar laws of heat and energy. They found that mass acts like energy, surface area like entropy, and surface gravity like temperature. Then, in 1974, Hawking showed that black holes should glow faintly with what we now call Hawking radiation, slowly losing energy over time. More than 40 years later, in 2016, the LIGO and Virgo collaborations detected ripples in space itself, gravitational waves from two black holes merging. For the first time, humanity had heard the sound of such a collision. Then, in 2019, the Event Horizon Telescope gave us the first image of a black hole's shadow, captured in the heart of a distant galaxy called Messier 87. It was a sight that had only ever lived in imagination until then. Today, we know of many black holes, some found through light, others through their silent pull on nearby stars. The Gaia mission has even spotted evidence of ones close to home, like Gaia BH1, about 1,500 light-years away. Though we've confirmed only a few dozen in our galaxy, scientists believe there may be hundreds of millions more, quiet, invisible, scattered through the night. The name black hole itself has a curious story. During a lecture in 1967, a student suggested the term, and the physicist John Wheeler adopted it. The phrase spread quickly, though it had appeared in print a few years earlier. Some say Robert Dick used it in the early 1960 seconds, comparing these cosmic traps to the infamous Black Hole of Calcutta. By 1964, newspapers were already speaking of black holes in space. However it began, the name stayed, and with it came a new way for us to picture the darkest hearts of the universe. To understand what a black hole truly is, imagine a place where the pull of gravity is so strong that even light, the fastest thing in the universe, cannot escape. The speed needed to get away, the escape velocity, is greater than the speed of light itself. In the language of physics, that means all the mass of the black hole is packed inside a boundary called the Schwarzschild radius, a limit that comes from Albert Einstein's equations of general relativity. Inside that line, space and time bend so sharply that every possible path turns inward. A calm, settled black hole is simple in its description, no matter how strange it seems. According to what scientists call the no-hair theorem, every mature black hole can be completely defined by just three things: its mass, its electric charge, and its spin. Apart from those, it has no other features that the universe can see. If two black holes share the same values for these three, they would appear identical from the outside, no matter how different their beginnings once were. Yet, researchers are still exploring how fully this rule applies. The real cosmos is messy, and there may be quiet exceptions hiding in the data. Each of those three traits leaves a mark that can be sensed from afar. A charged black hole repels or attracts other charges, just as a magnet might. Its total mass reveals itself through the pull of gravity, which bends the motion of nearby stars and light itself. The spin shows up through a strange effect called frame dragging, where the black hole's rotation twists the fabric of space-time around it, like honey swirling in a stirred cup. These clues let astronomers measure something that would otherwise be invisible. When an object falls toward a black hole, the details of what it once was, its structure, color, composition, vanish to the outside world. From the outside, that information seems to spread evenly across the surface of the event horizon. Physicists picture this horizon as a kind of thin, flexible film with resistance and energy flow. This model is sometimes called the membrane paradigm. Over time, the black hole calms into a simple state described only by mass, charge, and spin. Everything else, the original story of what fell in, is lost. That loss is so puzzling that it has become one of the deepest mysteries in modern science, the black hole information paradox. The simplest kind of black hole, one with mass but no charge and no spin, is called a Schwarzschild black hole. Carl Schwarzschild discovered the math for it in 1916, not long after Einstein proposed his theory. From far away, its gravity behaves just like that of any other round, heavy object, a planet or a star of the same mass. The idea that black holes suck in everything is true only very close to the edge. Farther out, their pull feels ordinary, just stronger. There are also more complex black holes. A non-spinning but charged one is described by what physicists call the Reissner-Nordstrom solution. A spinning but uncharged one is the Kerr black hole. The most general type, carrying both charge and spin, is known as the Kerr-Newman black hole. These are mathematical ways to describe how space and time behave around such extreme objects. Charge and spin cannot grow without limit. When they reach their maximum possible values for a given mass, the black hole is said to be extremal. Go beyond that, and the equation suggests something even stranger, a naked singularity, a point of infinite density exposed to the universe. But most physicists believe nature hides such singularities behind event horizons. This belief is called the cosmic censorship hypothesis. So far, all realistic computer simulations agree. Real black holes born from collapsing stars should have almost no electric charge, since stars are nearly neutral. But they do spin, often very fast. The black hole system, known as GRS 1915 plus 105, appears to be rotating at nearly the highest rate allowed by physics. The size of a black hole, defined by the radius of its event horizon, grows directly with its mass. For spinning or charged ones, that horizon shrinks a bit compared to a simple Schwarzschild black hole. In extreme cases, the horizon can sit very close to the singularity deep inside. The event horizon itself is perhaps the most haunting part of a black hole. It is an invisible boundary in space and time, a surface where the rules change completely. Once something crosses it, there is no path back out. Even light, the universe's fastest traveler, cannot escape. For an observer watching from far away, Any object falling in appears to slow down as it nears the horizon. Its clock ticks slower and slower, a phenomenon called gravitational time dilation. The light it emits stretches into longer, redder wavelengths, fading until it disappears altogether. To the outside world, it seems frozen in place, vanishing quietly into the dark. But for an observer who is actually falling in, the experience is very different. Their own clock runs normally. They would cross the horizon without noticing any sharp change. There would be no wall, no flash, no warning, just a steady drift into deeper gravity. This matches Einstein's equivalence principle, which says that freely falling feels the same as floating in empty space. The shape of a balanced event horizon is always roughly spherical. A non-rotating black hole's horizon is a perfect sphere. A spinning one flattens slightly at the poles and bulges around the middle, like a planet. At its core lies the singularity, a point, or in the spinning case, a ring, where our current laws of physics fail. It has no volume but holds all the mass, which means the density becomes infinite. Anyone who crosses the horizon of a Schwarzschild black hole faces a single direction of travel, inward. Rockets or engines could delay the fall for a moment, but never stop it. Near the center, gravity becomes so uneven that it stretches and tears everything apart in a process scientists call spaghettification. Objects are pulled into long, thin strands before being crushed completely. Their mass becomes part of the black hole's total. In spinning or charged black holes, the equations predict something different. The singularity may not trap everything completely. It could, at least in theory, connect to another region of space or even another universe. This idea has led to the concept of wormholes, and with them, the strange possibility of closed time loops. But most physicists think these paths can't survive real-world conditions. The slightest disturbance would collapse them. It's more likely that once quantum physics is fully woven into gravity, a goal not yet reached, these impossible structures will vanish from the math, replaced by something gentler and real. One proposed idea from string theory is called the fuzzball model. It suggests that instead of a single sharp core, a black hole is made of countless tangled strings of energy. There is no true horizon or singularity, only a dense web of quantum states. From far away, this bundle would still look and behave like the black holes Einstein described. But inside, the structure would be entirely different, softer, maybe even alive with motion. Around every black hole lies another curious boundary called the photon sphere. This is the region where light itself can circle the black hole, trapped in delicate balance. For a non-spinning hole, it sits about 1.5 times the Schwarzschild radius. A beam of light that happens to skim along it can orbit the hole, looping endlessly until even the smallest nudge sends it off course. If disturbed, the photon either spirals inward and disappears or escapes outward to freedom. Light that we see from this close comes from the thin layer between the photon sphere and the event horizon. In spinning black holes, or Kerr black holes, the photon sphere is not fixed. It depends on the direction of the black hole's spin and the path of the photon. If the photon moves with the spin, a prograde orbit, it circles closer to the horizon. If it moves against it, a retrograde orbit, it stays farther out. Spin also creates one of the most extraordinary features in all of astrophysics, the ergosphere. This is a region outside the event horizon where space-time is dragged around so violently that nothing can stay perfectly still. To resist being carried along, an object would have to move faster than light, which is impossible. The ergosphere touches the horizon at the poles, but bulges outward near the equator, shaped like a squashed sphere. Unlike the horizon, it is not a point of no return. Matter and light can still escape from it, and under the right conditions, energy can be pulled out of the black hole itself. This energy extraction happens through something called the Penrose process. A particle entering the ergosphere can split into two. One piece falls into the hole, while the other escapes with more energy than it had before, stealing a little from the black hole's rotation. Over time, this process can slow the spin. A stronger version, called the Blandford process, uses magnetic fields to do the same thing on a far greater scale. Many scientists believe this is what powers the bright jets we see shooting from the centers of active galaxies, where black holes feed and spin. Orbiting near a black hole is unlike anything in ordinary space. In Newton's universe, an object could orbit at almost any distance. But in Einstein's, there is a limit called the innermost stable circular orbit, or ISCO. This marks the closest distance where an object can circle the black hole without falling in. Inside this boundary, no orbit is stable. A tiny inward push sends the object into a final plunge. A small outward push might save it, letting it settle into a wider path. For a non-spinning black hole, the ISCO lies at a fixed distance. For a spinning one, it shifts inward for material orbiting in the same direction as the spin. Beyond the ISCO lies the plunging region, the final descent. Matter here can no longer resist the pull. It speeds up, rushing toward the event horizon at nearly the speed of light until it crosses that invisible line and vanishes forever from view. To an outside observer, the light fades and the story ends, but inside, time continues, quietly, in ways we can only imagine. For many years, black holes were seen as little more than mathematical curiosities, odd tricks of Einstein's equations that surely couldn't exist in the real sky. Even Albert Einstein himself doubted that nature would ever allow such a thing. He believed that as stars collapsed under their own gravity, their spin, the steady turning of their mass, would hold them up at a safe distance, preventing a complete collapse. That belief lingered for decades, and much of the scientific world quietly ignored the hints that black holes might be real. But a few physicists refused to let the idea go. They argued that black holes were not exotic mistakes, but natural outcomes of the same laws that shape planets, stars, and galaxies. By the late 1960 seconds, their persistence paid off. Nothing in the known laws of physics, it turned out, actually prevented the birth of an event horizon, the invisible surface beyond which no light can return. The mathematician Roger Penrose went further, proving that if such a horizon forms, then a singularity must exist inside it, a place where gravity grows without limit. Soon after, Stephen Hawking showed that the same mathematics also describes the beginning of the universe itself. Singularities, it seemed, were not just hidden inside black holes, they were part of our cosmic origin story. Around that time, discoveries like the Kerr solution for spinning black holes and the no-hair theorem began to show that these objects, though extreme, followed simple and elegant rules. The new field of black hole thermodynamics linked their behavior to the familiar laws of heat and energy. Slowly, black holes stopped being mysterious monsters and became objects that scientists could study, predict, and even measure. A black hole begins its life in the quiet death of a star. When a star runs out of fuel, it can no longer create the pressure needed to push back against gravity. The core grows heavier, the balance fails, and collapse begins. Sometimes this collapse is stopped by degeneracy pressure, a subtle push that comes from the quantum nature of particles. It can hold up lighter stars, creating white dwarfs or neutron stars. But for heavier ones, there is no rescue. If the leftover core of a star weighs more than about 3 times the mass of our sun, past what scientists call the Tolman-Oppenheimer-Volkoff limit, then not even neutron pressure can halt the fall. The star's outer layers are blasted away in a brilliant supernova, while its heart keeps collapsing until a black hole is born. Smaller remnants become white dwarfs, mid-sized ones, neutron stars, the heaviest, true black holes. The pattern of collapse depends on the star's original size. Stars more than 20 times the mass of the sun leave behind cores heavy enough to form black holes a few times the sun's mass. These are called stellar mass black holes. Yet the early universe, hot and crowded, may have produced far larger ones. In those ancient days, the first stars could have been hundreds of times heavier than the Sunday. When they died, they might have collapsed into black holes with hundreds or even 1,000 solar masses seeds that later grew into the supermassive black holes at the centers of galaxies. Some scientists think that, in the very beginning, even clouds of gas could collapse directly into enormous black holes without ever forming stars at all. Observations of distant quasars, brilliant beacons from the young universe, suggest that such gigantic black holes already existed when the cosmos was only a few 100 million years old. These objects may be the ancient ancestors of the dark giants we see today in galaxies like our own. To someone watching from far away, the creation of a black hole looks strangely slow. As the collapsing material nears the event horizon, time itself appears to stretch. Light from the falling matter becomes weaker and redder until it fades entirely. It's as if the material freezes just outside the boundary, forever trapped on the edge. Yet, from the viewpoint of the matter itself, the fall happens quickly, in moments. Two realities both true, depending on where you stand. Black holes need enormous densities to form, something that today happens only in dying stars. But in the very early universe, after the Big Bang, everything was far denser. That raises the possibility of primordial black holes, tiny black holes born not from stars but from the early fabric of the cosmos itself. For such objects to form, matter had to clump together rather than remain perfectly smooth. Small ripples in density, minute variations in the young universe might have been enough to start the process. Different theories of the early universe predict different sizes for these ripples, so no one knows exactly how many primordial black holes could exist. Despite the intense density of the early cosmos, it didn't collapse back on itself. The reason lies in the rapid expansion that followed the Big Bang. Space itself was stretching faster than gravity could pull things together. Modern inflation theory explains this as a kind of repulsive gravity, a negative pressure that drove the universe apart. It's why the same equations that describe a collapsing star can't be used to describe the expanding universe. One shrinks inward, the other stretches outward, rewriting space with every moment. Gravitational collapse, the implosion of a dying star, is not the only possible path to a black hole. In theory, if two massive particles collided with enough energy, the resulting compression could form a miniature black hole. By the early 2000s, however, no one had seen evidence of such an event. Not a trace of missing energy in high-energy experiments hinted that it might happen. This silence suggested there's a lower limit, a minimum size below which black holes simply can't exist. Theoretical physics places that limit near the Planck mass, an unimaginably tiny scale where quantum rules outweigh Einstein's smooth curves of space and time. At that scale, gravity and quantum mechanics must merge, though no one yet knows exactly how. If that limit is correct, then no process on or near Earth could ever create a black hole. Even our most powerful machines would fall far short. Still, some bold theories have imagined ways around that barrier. In certain versions of the universe, brain world models, for instance, the threshold might be much smaller, low enough that microscopic black holes could appear when cosmic rays hit Earth's atmosphere, or when particles smash together inside machines like the Large Hadron Collider. If that ever happened, such black holes would be tiny and fleeting. The math says they'd evaporate almost instantly, lasting for only a fraction of a second before disappearing in a whisper of radiation. So far, none have been found. The universe seems to keep its secrets well. Yet, even without these miniature versions, the story of black holes continues to grow. Once one is born, it can keep feeding, drawing in gas, dust, and unlucky stars that stray too close. Over millions of years, a small black hole can become enormous, gathering strength from everything that falls its way. Many astronomers believe this slow but steady feeding is how the great supermassive black holes at the centers of galaxies came to be. Others think there may be a middle stage intermediate mass black holes hiding in dense clusters of old stars. However they form, each black hole tells the same quiet story: gravity winning over light, space folding in on itself, time slowing to a stop. From the collapse of the first stars to the deepest centers of galaxies, they mark the places where the universe looks inward, forever holding the mysteries of what lies beyond that invisible line. Another way black holes grow is through merging. In the vast dark of the universe, they drift, drawn together by gravity, until they meet and combine. Sometimes a black hole merges with a passing star, swallowing it whole. Other times, two black holes spiral toward each other, their dance ending in a single, heavier object. Astronomers believe that this process was vital in the early universe, helping small black holes grow into the supermassive ones that now anchor galaxies. Each collision sends ripples through space itself, gravitational waves that echo across the cosmos. In 1974, Stephen Hawking made a discovery that changed how we think about these mysterious objects. He showed that black holes are not entirely black. Instead, they give off a faint glow, now called Hawking radiation. By applying quantum physics to the curved fabric of space around a black hole, Hawking found that particles can escape from near the edge, producing radiation like the gentle warmth of a perfect black body. Since then, many physicists have confirmed his equations through different methods, strengthening his remarkable insight. If Hawking was right, a black hole slowly loses energy as it emits this radiation. The smaller the black hole, the hotter and brighter it becomes. The larger it is, the cooler and quieter. For a black hole with the mass of our sun, the temperature would be about 60 nanokelvin, far colder than the faint cosmic background that fills the universe at 2.7 Kelvin. That means real black holes, the ones born from stars, actually take in more energy from the cosmos than they release. Instead of shrinking, they grow. To truly evaporate, a black hole would need to be much smaller, tiny beyond imagining, smaller than a grain of sand, with a diameter less than 1/10 of a millimeter. A black hole the mass of a car would shine for the briefest instant, blazing more than 200 times brighter than the sun before vanishing in less than a billionth of a second. Even smaller ones would disappear even faster, flickering out before a single heartbeat could pass. At such scales, the smooth curves of Einstein's gravity give way to the restless world of quantum physics. Some theories suggest that quantum effects might stabilize tiny black holes, allowing them to last longer. But so far, no evidence supports that idea. For the kinds of black holes that fill space, the ones made from collapsing stars or swirling gas, Hawking radiation would be so faint it would never reach our telescopes. There might be one exception. If ancient, primordial black holes exist, they would be tiny and extremely old. As they near the end of their lives, they could release a final flash of energy, a burst of gamma rays. Astronomers have searched for such flashes in the deep sky, hoping to catch the signature of a black hole's last breath. None have been found yet, which suggests that small, primordial black holes must be rare if they exist at all. NASA's Fermi Gamma Ray Space Telescope, launched in 2008, still watches for them, scanning the universe for those brief, silent goodbyes. If Hawking's prediction holds true, then even the biggest black holes will one day fade away. The process would be impossibly slow. A black hole as heavy as our sun would take around 10 to the 64th power of years to evaporate, a number so large it's almost meaningless beside human time. But that process wouldn't even begin until the universe itself cooled further, until the cosmic background dropped below the black hole's own temperature. Supermassive black holes are far more enduring. One with 100 billion times the mass of the sun would survive for roughly 2 times 10 to the 100th power of years. And the greatest of all those that may form when entire clusters of galaxies collapse would take around 10 to the 106th power of years to disappear. That is longer than any future we can truly imagine. For now, black holes remain as they have always been, dark, silent, and hidden. They give off no visible light, no radio waves, no heat that we can sense. The faint glow predicted by Hawking lives only in theory, so astronomers must look for them indirectly, watching how stars circle invisible companions or how light bends as it passes nearby. Each clue, each motion of matter and light, whispers of something unseen, a reminder that even in the deepest quiet of space, gravity still tells its story. The Event Horizon Telescope changed how we look for black holes. It isn't a single dish on a mountaintop, but a ring of radio observatories spread across the Earth, all listening together. Linked by precise timing, they act like one planet-sized instrument that can study the space right next to a black hole's event horizon, the invisible edge where even light cannot turn back. In April 2017, this network focused on the giant black hole in the galaxy, Messier 87 inches, the Virgo cluster. For about 10 days, 8 observatories on 6 mountains across 4 continents gathered faint, synchronized whispers from the sky. 2 years later, in April 2019, the team shared what they had pieced together, the first image of a black hole's shadow. The dark center wasn't the hole itself, but its silhouette light swallowed so completely that only a ring remained, a glowing halo of hot gas circling near the brink. That ring looked brighter on one side. The reason is Doppler beaming. Gas racing nearly at light speed shines more strongly when it moves toward us and dimmer when it moves away. Around such a massive object, matter must whirl at incredible speeds, well over 1,000 kilometers each second to avoid a direct fall. Gravity adds its own trick, bending light around the black hole. This gravitational lensing lets us see parts of the far side of the disk, as if the ring were folded into view. On the 12th of May 2022, the same project revealed an image of Sagittarius A*, the supermassive black hole at the heart of our Milky Way. The familiar ring and shadow shape appeared again, matching what Einstein's theory predicted. Yet the task was harder this time. Sagittarius A times is more than 1,000 times smaller and less massive than the monster in M87, so its glowing pattern flickers much faster. Turbulent plasma between us and the center of the galaxy blurs the view as well. Even so, the team captured the essential shape, a soft, bright ring wrapped around night. Years earlier, in 2015, the project had already hinted at what powers these regions. It found magnetic fields just outside the horizon of Sagittarius A times, some tidy and ordered, others tangled like threads in a storm. Theory had long expected such fields. The observations confirmed they were there, shaping how gas flows and how energy is released. In April 2023, astronomers went a step further by presenting an image that included not only the M87 black hole's shadow, but also the vast jet of high-energy particles blasting from its poles, tying the engine to the outflow in one picture. Another line of proof comes from ripples in space-time itself. On the 14th of September 2015, the LIGO detectors heard the first clear signal of gravitational waves, created when two black holes spiraled together and merged. One weighed roughly 36 suns, the other about 29. As they circled closer, the waves grew stronger and higher in pitch, then ended with a brief ringdown, the fading tone of a newborn black hole settling into shape. By reading the frequency and the way the signal died away, scientists could calculate the final mass and spin, and the numbers matched detailed computer models. The distance between the black holes right before the crash was only a few hundred kilometers, just a handful of Schwarzschild radii showing that nothing but black holes could fit so much mass in so little space. Since then, LIGO and its partners have recorded many more mergers, turning the study of black holes into a field with regular, direct detections. Closer to home, the orbits of stars tell their own quiet story. Near the center of the Milky Way, around the radio source called Sagittarius A*, astronomers have tracked about 90 stars since the mid-1990 seconds. Their paths swing fast and tight, revealing a hidden mass first estimated at a few million suns and later refined to roughly 4 million. All of that mass sits in a space smaller than a few thousandths of a light year. Nothing known besides a supermassive black hole can compress so much matter into such a tiny region. We can't see an event horizon directly here, but many hints suggest it must be present. Around such objects, gas doesn't fall straight in. Because of angular momentum, it spreads into a thin, hot disk, an accretion disk that shines as the gas rubs against itself. Friction in the disk pushes angular momentum outward and lets matter drift inward. As it falls, it sheds gravitational energy, heating to temperatures that can produce X-rays when the central object is a neutron star or a black hole. This process is astonishingly efficient. A large fraction of the infalling mass can be converted to energy far more than nuclear fusion manages in ordinary stars. Sometimes the disk and the black hole's magnetic fields combine to launch narrow jets along the poles, streams of particles moving at nearly light speed. We still don't know every detail of how these jets start, but many of the brightest events in the universe, quasars and other active galactic nuclei, draw their power from matter-feeding supermassive black holes. The glowing hearts of those galaxies are engines built from gravity, magnetism, and motion. On smaller scales, there are X-ray binaries, systems where a compact object pulls gas from a normal companion star. The gas glows in X-rays as it falls. If we detect pulsing or other direct signals from the compact object, it can't be a black hole. If no such surface signals appear, we study the companion's orbit to weigh the hidden partner. If the mass is above the maximum allowed for a neutron star, the simplest answer is a black hole. The first strong case, Cygnus X1, was reported in the early 1970 seconds. The companion star there is massive, which complicated the early measurements. But the evidence grew stronger with time. Today, some of the best mass estimates come from soft X-ray transient systems that flare for a few months, once every decade or two. Between flares, the disk dims and the companion is easier to measure. V404 Cygni is a well-known example. Sometimes, astronomers catch a more violent scene, a star passing too close to a supermassive black hole and getting torn apart by tides. Part of the star's gas falls into a new disk and lights up, producing a tidal disruption event that telescopes can watch as it rises and fades. In 2011, observers reported the first direct view of a quasar's accretion disk, a long-standing idea finally seen. Disks themselves can flicker in curious ways. In some systems, we see quasi-periodic oscillations, rhythms in the X-ray light at specific frequencies. These seem to come from matter moving near the inner edge of the disk, close to the innermost stable circular orbit. Because those frequencies depend on the mass of the central object, they give another route to weighing black hole candidates. At larger scales, entire galaxies show signs of the same engine. We call them active galaxies when their centers shine unusually bright or display distinctive spectral lines. The standard picture has three parts: a supermassive black hole in the middle, a hot accretion disk swirling around it, and twin jets shooting out along the poles. Only a handful of galaxies have been mapped in detail, but the list of strong suspects is famous. Andromeda, M32, M87, NGC 3115, NGC 3377, NGC 4258, NGC 4889, NGC 1277, OJ 287, APM 08279, plus 5255, the Sombrero Galaxy, and more. Over time, evidence has grown that nearly every galaxy, not just the active ones, harbors a supermassive black hole at its center. A tight link, called the M-sigma relation, connects the black hole's mass to the way stars move in the galactic bulge, hinting that galaxies and their central black holes grow together. Gravity offers other tests, too. Light bends as it passes a massive object, and we can watch for this bending in several ways. In weak lensing, the change is small, just a slight distortion. In microlensing, we don't see separate images at all. Instead, a star briefly brightens as something dark passes in front. Late in the 20th century, astronomers reported a few possible black hole detections via microlensing. In early 2022, they announced the first confirmed case of an isolated black hole acting as a lens, a single, silent mass, revealed only by the way it bent a background star's light. Even with all this, questions remain, especially for black holes the size of stars. We infer their presence from mass limits and the absence of a solid surface, but the extreme matter inside neutron stars is still not fully understood. Some theories suggest other exotic, compact objects could exist under the right conditions: quark stars, Q stars, even more speculative ideas like preon stars. These models try to explain certain observations without invoking a true black hole, yet general relativity sets strict upper bounds on how massive such stars could be. Many candidates exceed those limits. There's a counterintuitive fact about black holes that helps here. The average density inside a black hole's Schwarzschild radius actually goes down as its mass goes up. A supermassive black hole with 100 million suns could have an average density similar to water. That makes the physics of their formation easier to accept, and alternatives like packing a galaxy's center with many dark, compact objects instead of one supermassive black hole struggle to stay stable long enough to match what we see. Through the years, theorists have proposed exotic lookalikes, gravastars, black stars, dark energy stars. Each tries to mimic the signs of a black hole while replacing the interior with something new. They are interesting ideas and worth testing, yet the simplest story still fits the widest set of clues. Rings and shadows drawn by the Event Horizon Telescope, ripples heard by LIGO, stars whipping around an unseen center, disks that glow and flicker, jets that light the deep. Taken together, they sketch a single, quiet outline gravity, gathered so tightly that even light must bow, waiting at the heart of galaxies and in the remnants of dying stars, holding their secrets just beyond the horizon. In Einstein's theory, there is a curious mirror to a black hole called a white hole. A black hole has an event horizon that nothing can escape once it crosses. A white hole is the opposite. Nothing outside can ever cross in, yet matter, light, and even information could rush outward from it. In that sense, a white hole is the black hole's reflection across time. The idea appears in the math for eternal solutions, idealized black holes that have existed forever. In those solutions, the future contains a black hole region, and the past contains a white hole region. But the black holes we think are real form from collapsing stars, not from eternal setups. When we include the collapse in the equations, the white hole part disappears. No natural process is known that would create a white hole, and none has been observed. So for now, they live in theory. Some researchers have asked whether the biggest black holes, those at galaxy centers, could be linked to supermassive white holes. Stephen Hawking and others explored that possibility, though it remains speculative. If white holes exist at all, they should have measurable traits like mass, charge, and spin, just as black holes do. They would pull on their surroundings with ordinary gravity. The difference is the border. An object falling toward a white hole would never cross its horizon. The surface is one way in the opposite direction. In a specific idealized model called the maximally extended Schwarzschild solution, the past white hole horizon blends smoothly into a future black hole horizon. The geometry ties the two together. It helps to imagine how gravity behaves. On a planet, gravity is strongest at the surface and then weakens outward. For a black hole or a white hole, there is no solid surface at all. As you move inward, the pull grows without a final limit, because the center is a singularity, an edge of the theory where density becomes infinite and the usual rules fail. Quantum ideas add another twist. Hawking showed that black holes are not perfectly dark. They give off an extremely faint glow called Hawking radiation. In certain conditions, a black hole could sit in thermal balance with the radiation around it. If you reverse time in that balanced state, the math maps a black hole to a white hole. In that mirror view, the energy a black hole slowly emits by quantum effects resembles the natural outward flow a white hole would have. Later work in advanced frameworks, like the ADS CFT correspondence, echoed this time's symmetry. A black hole in anti-de Sitter space looks, on the boundary theory side, like an ordinary thermal system, and reversing time leaves the basic picture intact. The history of the idea reaches back to the early days of relativistic collapse. In the 1930 seconds, Robert Oppenheimer and Hartland Snyder used Einstein's equations to describe how a star could fall inward to form a black hole. Alongside that work, Thinkers such as John Leighton Synge considered whether the equations also allowed an opposite object that throws matter out. In 1964, Igor Novikov raised white holes explicitly, and Nikolai Kardashev developed the idea further. In the maximally extended Schwarzschild geometry, their presence is unavoidable. The same set of equations that gives you a black hole also gives you a white hole when you look across time. That extended space-time holds another surprise. It contains two separate exterior regions, two universes, linked by the overall structure. Particles can fall from either exterior into the central black hole interior, and, in principle, light from one exterior could be seen by an observer who entered from the other. In the opposite direction, particles can emerge from the white hole interior into either exterior. Space-time diagrams drawn in Kruskal-Sekaris coordinates show these regions elegantly. If you take a snapshot of space at a fixed time and draw how it curves, the picture looks like a narrow throat connecting two wide spaces. This is the Einstein-Rosen bridge, also called a Schwarzschild wormhole. Depending on which time slice you choose, the throat seems to connect two black hole horizons or two white hole horizons. Despite that inviting picture, the bridge cannot be used for travel. No one can enter a white hole from the outside, and anyone crossing a black hole horizon is carried to the singularity. The geometry closes the door either way. What looks like a tunnel is, in practice, a one-way drop or a one-way spray with no safe path through. All of this rests on an eternal, perfectly symmetric solution. Real black holes are born at specific times when stars die. When we model that birth by including the infalling stellar material, the white hole region vanishes from the story. The time reversal of a collapsing star would be a white hole that has existed since the beginning of the universe, steadily emitting matter until, in a final outburst, it disappears. The equations allow it, but nature may not. Most physicists think white holes are far less likely than black holes. Because we know how to make black holes, gravity does it in massive stars, while no clear formation path exists for white holes. Even if some white holes were written into the very first conditions of the Big Bang, they would be exquisitely unstable. The smallest disturbance could ruin the balance. A dust grain drifting inward, a photon with the wrong nudge, any tiny bit of infall would break the conditions that keep the white hole open. Instead of exploding outward, the system would trap the incoming matter in its gravity and shut down the outward flow. The delicate mirror would crack at the slightest touch, and yet the symmetry remains a useful guide. Thinking about white holes helps us test the edges of our theories, how gravity and quantum rules might meet, how time's arrow shows up in extreme settings, how horizons hide and reveal information. On paper, black holes and white holes are twins facing opposite directions, collapse answering expansion, future reflecting past. In the sky, we see only one twin, the one that pulls everything inward. The other, if it ever existed, would be a brief, fragile flare written into the first pages of time, gone before the universe had settled enough for us to notice. When scientists follow the strange math of black holes, they find that not all solutions look the same. The kind of black hole you start with changes the twin that shows up in the equations. For the simplest case, a Schwarzschild black hole, paths that seem to flow out of a white hole look as if they come straight from the hidden singularity, a place of infinite density where our current physics fails. But if the black hole carries electric charge, as in the Reisner-Nordstrom case, or spins rapidly, as in a Kerr black hole, the picture grows even stranger. In those solutions, a white hole is not a source in our own universe at all. It acts like the exit door of a black hole that belongs to somewhere else, another region. even another universe linked to us by a theoretical tunnel. That tunnel is a wormhole. It is a bridge the math allows, not a road anyone has walked. In every version of these stories, one rule remains strict. Nothing can enter a white hole from the outside. Its interior is sealed off. We could only watch whatever spills out, never reach in to test what is inside. Because no cause in our universe can set its output, a white hole would look unpredictable to us, what physicists call non-deterministic. The laws we use to forecast motion and light would not tell us what appears next at that horizon. There is a different kind of unpredictability called a naked singularity, a place of infinite density not hidden by any event horizon. Unlike a white hole, there is no forbidden shell you cannot cross. Some people compare the Big Bang to a naked singularity, since it seems to start the universe without a cover. But the match is not exact. A white hole is a time-reversed partner of a black hole. The Big Bang is the beginning of space and time as a whole. Black holes, by contrast, have a clear birth story. Massive stars run out of fuel, their cores collapse, and a horizon forms. They start at a moment and grow. White holes show no natural birth in our models. That makes them more mysterious and much harder to trust. If white holes exist, they would need either a special formation process or to have been present since the start of the universe. Neither option convinces most researchers. No telescope has found a mechanism that builds a white hole. Writing one into the universe at time zero would mean the cosmos began in an extremely special state without a good reason. Earlier, when astronomers first saw quasars, distant objects so bright they outshine their host galaxies, some thought white holes or continuous matter creation might be the engine. As data improved, the simpler answer won. A quasar is powered by an enormous disk of gas spiraling into a supermassive black hole. That story matches the spectra, the light curves, the radio jets, and the images. The white hole idea was set aside. Still, curiosity kept working. In the late 1980 seconds, a few scientists suggested a bold twist. Perhaps when a black hole forms, something like a local Big Bang can happen inside. The core would pass through a quantum transition, a regime where Einstein's equations yield to the rules of the very small and rebound instead of crushing to a point. The Einstein-Cartan-Siama-Kibble theory adds the effect of particle spin to gravity. At ultra-high densities, spin can create a repulsive term that stops a true singularity and forces a bounce. In that picture, the other side of the bounce is an expanding space, a baby universe. From inside that new universe, the parent would appear as a single bright white hole. Some people then asked a daring question. What if our own Big Bang was such a bounce? Not an explosive point, but a smooth restart after a collapse in a pre-existing cosmos. New models kept testing similar themes. In 2003, Joel Smoller and Blake Temple explored a shockwave picture in which the Big Bang behaves like an explosion inside a black hole, with the outward side appearing as a white hole to inner observers. In 2012, another group described the Big Bang as a small bang, a sudden ejection of all matter at once, and even guessed that some puzzling gamma-ray bursts short, intense flashes of high-energy light might come from brief white holes that flicker into being and vanish. In 2006, Alon Redder and Shlomo Heller suggested that the unusual event, called GRB 060614, could be such a case. In 2014, a different idea imagined our Big Bang as the outflow of a supermassive white hole erupting from a 5-dimensional vacuum. These proposals share a spirit, use time reversal or extra ingredients in gravity to swap a collapse for an outward flow. Most physicists remain cautious. Black holes are now observed in many ways through the orbits of stars, the glow of hot disks, radio jets, gravitational waves, and the ring and shadow images from the Event Horizon Telescope. White holes have no such evidence. They live in the math, not in the sky. The question, could white holes even exist, keeps returning because it touches deep puzzles. How time's arrow arises, how information is stored or lost, and how gravity and quantum rules meet. At the most basic level, a white hole is defined as the time reverse of a black hole. A black hole is the ultimate trap. Cross the horizon and nothing escapes. A white hole would be the ultimate fountain. Matter and light stream out, and nothing gets in. The two are mirror images, like inhaling and exhaling. The mirror comes from Einstein's equations, which, on their own, do not prefer forward time over backward time. If you play many physical processes in reverse, the equations still hold. In daily life, though, time has a direction. Heat spreads, eggs break, smoke disperses, and people age. This is the arrow of time, linked to the growth of entropy, the measure of disorder. Black holes fit that arrow. Things fall in. Disorder, in a precise sense, grows. A white hole seems to push the other way. It would release orderly streams that look like they came from nowhere. That conflict with the arrow of time is one reason many doubt white holes can form in nature. Even so, the mirror is useful. Stephen Hawking showed that black holes are not perfectly dark. Quantum effects near the horizon let them emit faint radiation. In special cases, a black hole can sit in thermal balance with its surroundings. If you flip time in that state, the equations map it to a white hole in balance. In anti-de Sitter space, the ADS-CFT correspondence links a black hole to a thermal system in a boundary theory. Reversing time leaves the thermal picture intact. These arguments do not prove white holes exist, but they keep the door open on the theory side. What about wormholes? The supposed tunnels that could connect a black hole to a white hole. The classic Einstein Rosen bridge appears in the maximally extended Schwarzschild solution. Draw the spacetime in Kruskal-Sekaris coordinates, and you see two outer regions connected through a throat. On some slices of time, that throat seems to link black hole horizons. On others, white hole horizons. It is a striking image, but it is not a highway. You cannot enter a white hole. And if you enter a black hole, you cannot steer away from the singularity. The throat collapses too quickly for travel, unless negative energy holds it open, and no known material provides the right kind in stable, macroscopic amounts. Because white holes refuse to show themselves, people look for indirect clues. Could a weird gamma-ray burst be a sign? Most bursts come from massive stars collapsing into black holes or from neutron stars colliding. A few events do not fit these patterns neatly, and a small group wonders if short-lived white holes could explain them. So far, the evidence is thin, but the search itself sharpens our tools. It pushes observers to ask whether any flash lacks a plausible parent, star, or merger, whether any burst arrives with a pattern that screams outflow with no inflow. The debate also circles back to Hawking radiation and the far future. If black holes lose energy slowly, could their final moment look white hole, like a last, intense outburst that releases what's left? Some models imagine a late-time pop, but the timescales are staggering. A black hole with the mass of a star, would need a number of years written with 60 plus zeros to evaporate. None of us, and none of our instruments, will see such an end. The idea remains a thought experiment for now. Underneath these discussions runs the question of cosmic censorship, the expectation that nature hides singularities behind horizons. If that rule holds, naked singularities and long-lived white holes should not occur in realistic collapses. Many simulations back this view, yet our knowledge is incomplete near the extreme densities where quantum gravity should take over. Approaches like loop quantum gravity and string theory try to merge the smooth fabric of space-time with the grainy world of quanta. Some versions naturally replace singularities with bounces or fuzz and make wormholes or white hole-like phases less pathological. Others do not. Until a full theory is tested, the door cannot be fully closed. To make the picture feel less abstract, simple images help. A black hole is like a whirlpool in a river. Drift too close, and you are drawn in. A white hole would be like a hidden spring, forcing water outward in a steady jet that you cannot swim into. Think of an archerfish spitting a stream to knock an insect from a branch, or of a volcano that only erupts outward. No one can climb into the vent during the blast. These are only analogies, and they all fail in some way, but they give the mind a handle. One object gathers, the other expels. Over the last century, the balance between theory and observation has shifted again and again. Black holes moved from chalkboards to telescopes and detectors. We have seen their shadows, heard their mergers, and watched their disks and jets. White holes have not made that journey. Most astronomers and physicists now treat them as mathematical curiosities, clean sketches that the universe does not seem to draw. Still, the idea has value. It makes us check how time's arrow appears in gravity. It drives us to ask whether information can be lost or must always be preserved. It invites new links between thermodynamics, quantum fields, and curved spacetime. So, the work continues on two fronts. Some researchers refine the equations, exploring whether loop quantum gravity, string theory, or related models can make white hole-like phases natural and stable. Others watch the sky for anything that cannot be explained by known engines. A burst with no progenitor, a jet without a feeding disk, a flash that rises and falls in a way our current maps cannot match. Until such a sign appears, white holes remain part legend, part lesson shapes that help us test what we think we know about time and gravity. They linger at the edge of our theories, where math can still surprise us, and where the universe may yet have another story to tell. Where might a white hole appear? The question sits at the edge of what we know about space, time, and gravity. The name itself comes from Einstein's math, not from anything a telescope has seen. Black holes leave many signs: stars whipping around invisible masses, hot gas glowing in X-rays, ripples in space-time from mergers. White holes leave none. On paper, they are the mirror of black holes. Instead of pulling everything in, they would pour matter and light outward and never let anything cross in. People who study the early universe sometimes look there first. Our cosmos began about 13.8 billion years ago in a state so hot and dense that ordinary rules blur. In the first fractions of a second, energy flickered, space stretched, and tiny quantum jitters shook the young fabric of reality. In that brief, violent dawn, some imagine that white hole-like eruptions could have flashed into being short outbursts that pushed matter outward before fading. If such flashes happened, they might have seeded patterns we still see today. the cosmic web of filaments and clusters that spreads across the sky. A few have even wondered whether unknown signals like fast radio bursts, sharp radio blips from faraway galaxies could be linked to white hole events. Most researchers favor other causes, yet the door stays cracked open because the early universe is still full of mysteries. The second place to look is the quantum world. On the smallest scales, space is not smooth. It fizzes with tiny fluctuations where pairs of particles appear and vanish. If quantum jitters can make particles, could they also make tiny white holes? These would be minuscule, smaller than atoms, and they might last only an instant. Even so, if nature can make micro white holes at all, then white holes would be more than a quirk of math. This mirrors the idea of primordial black holes, hypothetical small black holes formed right after the Big Bang when some patches were denser than others. If primordial black holes are possible, maybe primordial white holes are, too. Some bold models even ask whether strange compact objects in large numbers could help explain dark matter. Evidence is thin, but the thought experiments help push theory forward. A third path links white holes to black holes directly. In some clean solutions to Einstein's equations, a black hole on one side comes with a white hole on the other. In the simplest case, the Schwarzschild solution, space-time can be extended so that paths of light or matter emerge from a white hole region while others fall into a black hole region. In more complex solutions charged black holes, Reisner-Nordstrom, or spinning ones, the geometry allows multiple connections. On paper, it can look like a bridge between regions, a wormhole. In stories, a wormhole is a tunnel you can travel through. In physics, the tunnel collapses unless something with negative energy holds it open, and no such stable substance is known. The math is a guide. Nature may not follow. Even if a white hole appeared, how long could it last? A black hole can endure for ages, slowly losing mass by Hawking radiation. A white hole, by definition, refuses to take anything in. Once it finishes pouring out what it has to give, it might simply vanish. That would make it unstable in a universe filled with stray particles and light. The slightest incoming nudge could break the balance. Some proposals picture a more patient story. In Loop, Quantum Gravity, space is made of tiny loops, and collapse may never reach a true singularity. The core could bounce, turning an inward fall into an outward flow. In that view, a black hole might end as a white hole, releasing its stored energy and information. If so, white holes could be the final chapter in black hole lives. Only the timescales are beyond imagination. A wilder step asks whether our entire universe sits inside a white hole. The Big Bang, in this picture, would be the outward side of a larger structure, possibly linked to a black hole in a parent universe. Variations on this theme include shockwave models and small bang ideas, and even speculations that some rare gamma-ray bursts might mark a brief white hole appearing and fading. Most data point to well-known engines, collapsing stars, and neutron star mergers, but a few odd bursts keep theorists busy, testing where the standard stories bend and where they break. To understand why the debate is so hard, it helps to go back to first principles. In Einstein's theory, the basic equations are time-symmetric. If you can describe a process going forward, you can flip time and still have a valid solution. A black hole is a one-way door inward. Flip time, and you get a one-way door outward. Everyday life, however, is not symmetric. We feel the arrow of time because entropy, the measure of disorder, tends to grow. Heat spreads, glasses shatter, smoke disperses. Black holes fit that arrow. Things fall in, and from the outside, the details seem to vanish, raising the information paradox and the question of how nature keeps its books. White holes would look like the opposite, matter and light flowing out as if from nowhere. That clash with the arrow of time is one reason many doubt they can form in the universe we see. Still, the mirror teaches us. Hawking showed that horizons are not perfectly quiet. Quantum effects let black holes glow very faintly. In certain balance setups, reversing time maps a black hole in thermal equilibrium to a white hole in thermal equilibrium. The AD-CFT correspondence carries a similar lesson. A black hole in a special curved space looks like a hot, ordinary system in a lower dimensional theory. Reverse time, and the thermal story stays consistent. These arguments don't give us a white hole in the sky, but they show why the idea keeps returning whenever we try to stitch quantum rules to gravity. The where question also touches observation. If white holes existed today, they would be unruly neighbors. Because they can't swallow anything that hits them, they would be easy to disturb. A single dust grain drifting in could spoil the outward flow. That makes large, long-lived white holes unlikely in a universe filled with matter and radiation. If any appear, they should be brief and bright sudden flashes that fade quickly. Gamma-ray bursts remain a natural place to look, but the best-studied bursts already match known engines. The search continues because a single true outlier could change the story. White holes sit in the middle of the information debate as well. Quantum mechanics says information is never destroyed, yet black holes seem to hide it behind horizons and perhaps drop it into singularities. If a black hole ends as a white hole, then the information might come back out in a new form. Some models try to make that idea precise. Others argue the information is encoded in subtle patterns at the horizon and never truly lost. Either way, white holes help frame the question and keep theorists honest about what their equations imply. Simple images can make the abstract feel closer. A black hole is like a whirlpool. Get too near and you are drawn in. A white hole would be like a hidden spring, pushing water outwards so strongly you cannot swim in. Think of a puffball mushroom puffing a cloud of spores into the air, a sea cucumber ejecting material as a defense, or a bombardier beetle releasing a hot chemical spray. Each is a one-way out moment. The parallels are loose and imperfect, yet they give the mind something to hold while the math does its work. All of this grows from Einstein's new way of seeing gravity. Newton imagined a force pulling across empty space. Einstein replaced the force with geometry. Mass and energy bend the fabric of space-time, and objects follow the curves. His field equations are elegant and strict, and tucked inside them are strange possibilities. Black holes, white holes, and the bridges between regions we call wormholes. In 1916, Karl Schwarzschild found the first exact black hole solution, with an event horizon and a singularity at the center. For years, even the founders doubted such objects were real. Later, Robert Oppenheimer and Hartland Snyder showed how a heavy star can collapse past any rescue and form a horizon. If collapse is a valid solution, time reversal gives its partner, matter and light streaming outward from a region that admits nothing in. The record since then has favored the inward door. We have watched stars dance around a dark mass at the center of our galaxy, weighed invisible companions in X-ray binaries, seen jets launch from bright accretion disks, heard the ring of merging black holes, and imaged a black hole's shadow as a ring of light around darkness. For white holes, we have stories, equations, and a few creative guesses in old data, but no clean signal. That absence shapes the odds, though it doesn't close the case. The right theory of quantum gravity might change the rules near extreme densities, replacing singularities with bounces and making outward phases possible under special conditions. So the question, where could a white hole appear, keeps science honest. It points us to the early universe, to the quantum foam, and to the hidden interiors of black holes. It asks whether bridges through space-time can ever be more than drawings, whether the arrow of time is woven into gravity, and how information survives when horizons form. It may be that white holes never light our sky. Even then, they do useful work in the background, shaping tests for new ideas and reminding us that equations can see farther than our instruments. And if one day a short, unearthly flash arrives with no source we can name, the old mirror will be waiting, ready to be held up against the night. White holes remain creatures of mathematics. No telescope has ever seen one, and many physicists doubt they could form in nature. Yet on paper they stand beside black holes as valid solutions of Einstein's equations. The connection between the two becomes sharper when we bring in wormholes, bridges that the equations allow between distant regions of space and time. In 1935, Albert Einstein and Nathan Rosen found a solution that looks like a tunnel linking two space-time regions. Later, people began calling this tunnel an Einstein-Rosen bridge, and then more simply, a wormhole. A picture helps. Imagine space as a sheet of paper. You can crawl across the surface from one corner to the other, or you could fold the sheet so those corners touch and poke a hole through. The shortcut is the wormhole. In principle, such a tunnel could join a black hole to a white hole, letting matter fall in on one side and spill out on the other. Stories and films love this idea, but the physics is stern. Most calculations say a natural wormhole would snap shut so fast that nothing could pass through. To hold it open, you would need exotic matter with negative energy density. Quantum theory hints that tiny amounts of such effects exist, but nothing large or stable enough has been found. These fanciful shapes do not come from daydreams. They come from the same field equations that have passed test after test. Starlight bent around the sun in 1919 just as Einstein predicted. Clocks tick more slowly in stronger gravity. In 2015, LIGO heard gravitational waves from merging black holes, ripples that general relativity foretold a century earlier. In 2019, the Event Horizon Telescope produced the first image of a black hole's shadow, a dim ring framing darkness in the galaxy M87. The math that admits wormholes is the math that explains all of these. Singularities sit at the heart of this story. A singularity is a place where the equations break, density goes to infinity, and our known laws give no answer. For a black hole, the singularity lies in the future of anything crossing the horizon. It is the end of the road. For a white hole, the singularity would be in the past, like an initial blast that sends matter outward. Some writers compare the Big Bang to a white hole-like event, though the match is not exact. The early Einstein-Rosen bridge itself is not a permanent door. It collapses too quickly for information to cross. In the 1,950 seconds and 1,960 seconds, John Wheeler and others searched for ways to stabilize a traversable wormhole, and Wheeler later gave us the name black hole, an elegant replacement for frozen star, or collapsar. Meanwhile, observations piled up on the black hole side. We now have strong evidence for stellar mass black holes, only a few times heavier than the Sun, and for giants millions or billions of times heavier, sitting at galactic centers. Our own Milky Way hosts Sagittarius A*, about 26,000 light-years away. weighing in at around 4 million suns. The M87 image showed a glowing ring of hot gas wrapped around a deep shadow, just as the theory sketched. For white holes, we have no such signals. They still serve a purpose, though. They remind us that Einstein's equations are symmetric in time, while our lived world is not. That brings us to the arrow of time. The basic equations let you run the film forward or backward and still get valid physics. But daily life does not work that way. Heat spreads, cups shatter, smoke disperses, entropy grows. Black holes fit this arrow. From the outside, things go in and do not come back out, and the details seem to vanish, raising the puzzle of what happens to information. Stephen Hawking showed that horizons are not perfectly quiet. Black holes emit a faint thermal glow due to quantum effects. Over inconceivably long times, this Hawking radiation lets a black hole lose mass and evaporate. Some speculative models imagine the very last stage looking white hole like a final release of energy and information. We do not know if the universe allows that ending, but the proposal shows how the inward door and the outward door might be tied. When ideas stray toward the unbelievable, it can help to borrow gentle images from life. Nature hosts creatures that stretch our sense of what is possible, much as relativity stretches our ideas about space and time. A pistol shrimp snaps its claw and makes a bubble so hot it flashes with light. A tardigrade survives vacuum, cold, heat, and years without water. We are used to thinking the sea has limits, yet the deep holds anglerfish that live where sunlight never reaches. A black hole is like that abyss, dark, patient, swallowing whatever drifts too near. A white hole, if it exists, would be more like a bombardier beetle brief, directional, ejecting hot streams that nothing can push against. And a wormhole could be compared to the Arctic tern's vast migrations, cutting across the world in paths that look like shortcuts from above. The analogies are not perfect, but they help the mind walk alongside the math. Time's arrow returns again and again. A black hole feels like an ending, a quiet grave where stars, gas, and even planets meet a one-way boundary. A white hole reads like a beginning, a sudden release, a fountain that nothing can enter. If you place the pair together, you see how our ideas about end and start may be woven into space-time itself. The boundary of a black hole, the event horizon, is a one-way door inward. Cross it and you cannot return. The white hole flips the sign. All flow is outward and the door is locked from the other side. In the equations, both shapes appear. In the sky, only one has shown its face. The history behind these shapes is simple and strange. Einstein's 1915 field equations replaced Newton's distant pull with the geometry of space-time. Mass and energy bend the fabric. Objects follow the curves. In 1916, Karl Schwarzschild, working at the front during the First World War, found the first exact black hole solution, complete with a horizon. For decades, many thought this was a trick of symbols. Then, Oppenheimer and Snyder showed how heavy stars collapse past any rescue, and theory began to align with nature. The same time symmetry that gives you a black hole gives you its mirror when you flip the film. The mirror is rigorous in math, elusive in reality. Even so, the mirror keeps opening doors for our thinking. Could some black holes end as white holes, returning what they took in? Could a wormhole ever be held open by quantum effects we do not yet understand? Could the Big Bang share features with an outward phase on the far side of a bounce? Each question pushes at the border where gravity and quantum rules meet. Approaches like loop, quantum gravity, and string theory try to merge the smooth fabric of general relativity with the grainy world of quanta. Some versions replace singularities with bounces, others do not. Until a full theory is tested against data, the question stays alive. We can also return to observation and ask what a white hole would look like if one flashed in our universe today. Because it cannot swallow incoming matter, it would be fragile. A single dust grain could spoil its balance. That fragility makes long-lived white holes unlikely in a cosmos full of gas and radiation. If any appear, they would likely be brief and bright, short eruptions that fade fast. Astronomers study gamma-ray bursts, the most powerful explosions we see, and most of them fit known engines, collapsing massive stars or colliding neutron stars. A few odd cases keep debate going, but nothing points clearly to a white hole. Even as the evidence weighs against them, white holes continue to earn their place in the conversation. They force us to say what we mean by time's direction, by information, by cause and effect. They remind us that the equations we trust to guide spacecraft and predict eclipses also predict things we have not yet seen and may never see. In that way, white holes are less like promises and more like questions we are not finished answering. Think of the monarch's life to bring the ideas back to ground. An egg becomes a caterpillar, then a still chrysalis, then a winged butterfly. One form ends, another begins. The stages are opposites and yet part of the same story. Black holes and white holes, in theory, sit like that in the fabric of space-time, end and beginning laid side by side. We read the universe in endings now because those are what we can see and measure. Shadows around darkness, rings of hot light, waves in space-time, stars circling an unseen mass. Beginnings may be hidden from us, or they may not exist in the way the math suggests. Either way, the pair helps us keep time's arrow in view while we work. So we keep both eyes open, one on the chalkboard where equations sketch mirrors and bridges, and one on the sky where instruments test what nature allows. Black holes have walked out of theory and into observation. White holes, for the moment, remain a soft whisper at the edge of the page, purely theoretical, tightly reasoned, and still unconfirmed. They hold their place not as things we can point to, but as ideas that let us ask better questions about the universe's structure, the fate of information, and the quiet, one-way drift we call time. The second law of thermodynamics is one of the surest guides we have. In any isolated system, disorder, what scientists call entropy, tends to increase, or at least stay the same. You can picture it with a simple fire. A log has neat, stored energy in its bonds. Burn it, and you get heat, smoke, and ash. The heat spreads, the molecules move faster, the tidy structure is gone. Ice melting, iron rusting, a star burning its fuel, all follow the same rule. Energy moves from concentrated and organized to scattered and mixed. Set that beside a strange idea from gravity. Black holes are real objects where gravity is so strong that nothing, not even light, can get out once it crosses the event horizon. Their mirror image in the math is a white hole. Nothing can go in, and matter and light only come out. Think of a one-way fountain that refuses to take anything in return. Such an object, if it existed, would raise a hard question. Would a white hole break the second law? To see why this matters, remember how black holes entered thermodynamics. For a while, people thought a black hole was almost featureless, a perfect swallow that never gives back. Then, Jacob Bekenstein argued that black holes must carry entropy. If you drop something with entropy into one and the universe doesn't keep track, the second law would be broken. Stephen Hawking went further and showed that black holes should glow faintly with particles now called Hawking radiation. That glow gives them a temperature, which means they have entropy. Even more surprising, a black hole's entropy scales with the area of its horizon, not its volume. Gravity, quantum theory, and heat all shook hands in that single idea. What, then, about a white hole? Run Einstein's equations backward in time and a black hole turns into a white hole. Math allows both. But nature cares about the arrow of time, and entropy is how we feel that arrow. A glass falls and shatters. Shards never jump back together on their own. White holes look like that movie played in reverse. Particles would fly outward in just the right pattern to reconstruct a precise past that seems to fight the rule that disorder grows. Some scientists argue that a true white hole would require entropy to drop, at least locally. The outward spray would have to be fine-tuned in a way that looks unnatural. It would be like smoke gathering back into a cigarette or scrambled sound rearranging itself into a perfect song. Others suggest a wider view. The second law counts the whole book, not a single page. If a black hole later becomes a white hole only after a long life of swallowing matter and radiating heat, the total entropy might still go up. The last burst would be the end of a long process where the universe kept adding disorder all along. This is where quantum gravity ideas enter. General relativity handles the large-scale flow of space and time. Quantum mechanics rules the very small. We still lack a finished theory that unites them. Loop quantum gravity, explored by Carlo Rovelli and others, pictures space as made of tiny loops. In that view, a collapsing star might not end in an infinitely dense point. Instead, the core could bounce. The bounce could appear to us as a white hole. If so, the second law would not be broken. Entropy would not vanish. It would move from the quiet storehouse of a black hole to a messy cloud of particles spreading outward. Even then, puzzles remain. What is the entropy of a white hole? A black hole's entropy is tied to its horizon area. A white hole, by definition, lets nothing in. Does that mean no entropy? Or does it inherit the entropy of the black hole it once was? Some think it should carry the same entropy because the information that fell in is not destroyed but is stored in hidden ways and later released. This links to the black hole information paradox. If information cannot be lost, and quantum theory says it cannot, then something must carry it back. A late-time white hole phase could be the carrier, letting the universe keep its books without cheating. A simple image helps. Spill coffee on the floor and it spreads into a stain. You never expect it to leap back into the cup drop by drop. That is entropy at work. A white hole would look like the opposite. A stain gathering itself into a perfect pour with no spill. It feels wrong because almost nothing in daily life runs that way. Yet the equations of gravity do not pick a direction. What breaks the tie is how the universe began in a state of very low entropy. Since then, disorder has been rising. If the cosmos had started high and stayed high, the arrow of time might feel different to us, and white holes might not seem strange at all. Some have even asked if the Big Bang was like a white hole. All matter and energy came outward. Nothing could go in. In spirit, it resembles the definition. If that grand beginning did not break the second law, perhaps smaller white holes need not either. The difference is context. The Big Bang set the initial low entropy stage. A small white hole today would appear inside a universe already far along the road to disorder, which is harder to reconcile. Numbers offer another view. The entropy of a black hole with the sun's mass is about 1077 inches, Boltzmann's units staggeringly large compared with the sun's normal radiation. When a star becomes a black hole, the entropy jumps. That fits the second law. If that black hole later turned into a white hole and returned its contents in a neat, ordered way, entropy would drop, which is not allowed. So any realistic white hole would have to release matter chaotically, with no hidden pattern, so that entropy continues to grow. The outward flow must look random, like steam billowing, not like a movie rewinding. Some computer models play out this last act. As a black hole shrinks toward the Planck scale about 10⁻35 meters, it might not quietly vanish. It could erupt, behaving like a tiny white hole for an instant. The result would be a messy burst of particles and radiation, adding to the universe's disorder, not subtracting from it. From far away, it would look less like a rewind and more like a final firework. Even so, we have never seen such a thing. White holes remain on paper, black holes do not. We have imaged a shadow in M87, watched stars whip around Sagittarius A*, and heard mergers ring through spacetime. A few have wondered whether certain short gamma-ray bursts could be signs of white holes. So far, the data favor known engines like collapsing stars and colliding neutron stars. The white hole option has not found a clean case. There is one last angle to keep in mind. The second law is statistical. It does not forbid rare dips in entropy outright. It says they are fantastically unlikely. A glass could, in principle, unbreak, but you would wait longer than the age of the universe to see it. A white hole might not be strictly impossible. It might simply be so improbable that nature almost never draws that card. The equations allow the shape, the odds keep it out of sight. So we end where we began, with a quiet rule about disorder and time. The second law gives our days a direction and gives stars their fate. Black holes fit inside that story more easily than their mirror twins. If white holes exist at all, they likely live as brief, unstable flashes, or as the last pages of a black hole's long book, written in chaos so the accounting of entropy still balances. And if they never show themselves, they still earn their keep by sharpening our questions about information and memory, about the first moments after the Big Bang, and about how the deep laws of heat and gravity agree on the flow of time. Gravity is the oldest story we tell about the sky, yet it still keeps its deepest page hidden. Newton gave us a clean rule for orbits and tides. Einstein showed that gravity is the bending of space and time themselves. Quantum mechanics, meanwhile, explains the jittery world of atoms with uncanny accuracy. But when we try to make these two great stories agree, they argue. Somewhere between the smooth curves of relativity and the grainy jumps of the quantum, a missing chapter waits. We call that chapter quantum gravity. Now imagine two black holes, each many times heavier than our sun, circling tighter and tighter until they collide. Space itself ripples. Those ripples, gravitational waves, were first heard in 2015 by LIGO, proving Einstein's prediction from a century earlier and opening a new sense for astronomy. A collision like that is not just fireworks. It is a natural experiment, far beyond any machine we can build. The energies are enormous, billions upon billions of times higher than proton smash-ups in the Large Hadron Collider. When nature pushes the laws that hard, cracks may show, and in those cracks, hints of quantum gravity may appear. Relativity describes gravity as a smooth fabric that bends under mass and energy. Quantum theory says the small world is restless and discrete, ruled by chance. If space-time itself is quantum, then at unimaginably tiny scales, the Planck scale, far smaller than any atom, the fabric may foam and flicker like boiling water. No telescope can see that directly, but the most extreme events in the universe, like black hole or neutron star mergers, may carry its fingerprints in their waves. Think of how elephants listen. They can sense faint tremors through the ground from kilometers away, learning about storms and distant herds long before their eyes could. Gravitational wave detectors are like that. LIGO and Virgo measure changes in length smaller than a fraction of a proton, turning the quiet tremble of space-time into sound. A typical signal begins low and soft, rises in pitch and volume as the two bodies spiral in, then ends in a brief ring as the new black hole settles. General relativity predicts this chirp with sharp precision. If quantum gravity leaves a mark, it might show up as tiny irregularities, subtle echoes, extra wiggles, or a ring that fades at slightly the wrong rate. Finding such features would be like spotting new footprints on an uncharted trail. Some ideas say the center of a black hole is not a true point of infinite density. Infinities often mean we are using the wrong tools. Quantum gravity might smooth the core into something physical, a fuzzy ball of quantum fields, a tangle of strings, maybe even a wormhole. If that is true, the final ring, after a merger, the quasi-normal modes could differ slightly from Einstein's forecast. Teams now sift the data for these tiny differences, treating each collision as a test bench for the deepest laws. Others look to the horizon itself. In relativity, a horizon is smooth and absolute. Cross it, and you cannot return. Quantum ideas hint at structure. Some propose firewalls, energetic layers that would burn anything trying to pass. String theory suggests fuzzballs, where the entire black hole is made of tangled strings with no empty interior at all. If horizons are not perfect, then the waves from a merger might carry small afterbeats, like the extra ripples you see when a stone hits reeds instead of open water. Neutron star collisions add their own clues. A neutron star is the crushed core of a massive star, so dense that a teaspoon of its matter would weigh billions of tons. When two of them collide, they send both gravity waves and light, gamma rays, X-rays, radio afterglow, even visible flashes. In 2017, telescopes caught such an event and saw heavy elements, gold, platinum being forged. Matching the gravity signal to the light lets us probe matter at densities and pressures no lab on Earth can reach, and it lets us check relativity under stress. Why chase these tiny deviations? Because uniting quantum rules with gravity has been a goal for 100 years. String theory, loop quantum gravity, and other frameworks give possible answers, but experiments must decide. If LIGO, Virgo, Kagra, or the next generation Einstein telescope and Cosmic Explorer find even a small mismatch with relativity, it could point the way. A hint in one waveform, repeated across many events, would be the first experimental nudge toward quantum gravity. The search is patient work. Gravitational waves are whispers in a storm. Detectors must be isolated from earthquakes, traffic, and wind. Lasers must be ultra-stable. Mirrors must be hung on delicate suspensions. After that comes data triage, months of sorting to separate real signals from noise. Here, the animal world offers another image, the pangolin. It cannot see the insects it hunts, hidden deep in nests and logs, but it keeps digging with careful claws until it finds them. Physicists do the same with the data, confident that the patterns they seek are there, just faint. Some theorists predict echoes after a merger. In Einstein's picture, the newborn black hole rings like a bell and quiets. If the horizon has structure, waves could bounce and return as a second, lighter pattern. A few teams have claimed tentative signs. Others see only noise. The jury is still out. But the method is clear. Listen for the offbeat, the extra tap on the drum that relativity does not expect. All of this touches old questions we keep asking in new forms. What is space made of? Is time continuous or built from tiny steps? What happens past the horizon? Are there hidden dimensions? Collisions push our theories to their limits, the way a cheetah pushes muscle and bone to reach astonishing speed. Watching that sprint tells you how an animal is built. Listening to black holes collide tells you how the universe is put together, its skeleton of space-time, its nerves of gravity. New instruments will widen our hearing. LISA, a space mission planned for the 2030 seconds, will follow Earth around the sun and listen for lower frequency waves from supermassive black hole mergers, events millions of times larger than those we've heard on Earth. Pulsar timing arrays, which track the regular radio ticks of spinning neutron stars spread across the galaxy, have already hinted at a background hum of waves from many distant giants. Each method is another instrument in the cosmic orchestra. Together, they play music our species has never heard before. For most of history, we studied the universe only with light, first by eye, then with radio dishes, X-ray satellites, and infrared cameras. Gravitational wave astronomy adds a second sense. It lets us feel cosmic motion, not just see it. That change is as deep as a person born deaf, learning to hear. Whole structures, hidden collisions, silent giants suddenly step into view. None of this takes away from Einstein. He knew his theory was not the final word, just a masterwork that would need a frame. Newton's laws still guide spacecraft, even though relativity refines them. Relativity guides GPS in your phone, correcting for time's flow in Earth's gravity. Quantum mechanics gave us semiconductors and lasers. Quantum gravity may feel abstract now, but new understanding often grows into new tools. We cannot guess which ones. No one reading about wave functions in the 1,920 seconds foresaw smartphones. The animal world helps us imagine how to adapt our thinking. An octopus has no bones, yet squeezes through tiny cracks, hides by shifting color, and even uses tools. Nature finds paths we never expect. The universe might do the same. Maybe space-time is woven from loops, as loop quantum gravity suggests. Maybe it's built from vibrating strings with extra dimensions curled too small to see. Maybe it's something we have not named. Black hole and neutron star collisions may be the first crumbs leading into that forest. There is also humility in this hunt. We may find that relativity holds perfectly in every wave we can measure, and that quantum gravity leaves no mark we can hear at those scales. That would still teach us where not to look, or what precision we must reach. More likely, the truth will come in small steps. A slight mismatch in a ring down here, a repeated echo there, a neutron star merger whose glow and gravity disagree by a hair. Each hint will demand better detectors, cleaner analysis, and many more events. So we keep listening. The ground-based observatories will improve. New ones will rise. LISA will open the low-frequency sky. Pulsar arrays will refine the background hum. Somewhere in that growing symphony, a small note may drift in that Einstein did not write. It will not erase the old music. It will add a new line, the beginning of that missing chapter. And when we read it, the story of gravity may finally include the quantum bringing the smooth and the grainy, the continuous and the jumpy onto the same page. Until then, each ripple we record is a gift. It tells us about black holes and neutron stars, about how elements are forged, about how galaxies grow. It also tells us how far our instruments and our patience have come. A century ago, gravitational waves were words on paper. Today, they are signals we can chart and share. Tomorrow, they may carry the first clear hint of quantum gravity, the small deviation that shows us where the next theory begins. Quietly, steadily, we listen for it in the dark, the way elephants listen for thunder, confident that the ground will speak. Matter is everything we touch and see: the air in our lungs, the ground beneath us, the stars far away. Antimatter is its mirror image. Every particle of matter has a twin with the same mass but an opposite electric charge. When they meet, they do not simply pass through each other. They destroy one another in a small burst of energy. Scientists have long wondered whether this destruction is perfect, whether all of their properties cancel, leaving nothing but light behind. The story starts at the smallest scale, with atoms. Early in the 1900s, physicists discovered that atoms are made of protons, neutrons, and electrons. Protons carry positive charge, electrons negative, and neutrons are neutral. In 1932, the English physicist Paul Dirac developed equations linking quantum mechanics and relativity. His math predicted that there should be particles identical to electrons, but with opposite charge. Soon after, that particle was found in cosmic rays. It was the positron, the first known piece of antimatter. Over time, other antiparticles followed: antiprotons, antineutrons, and even atoms of antihydrogen made from a positron orbiting an antiproton. Scientists can create them in particle accelerators like those at CERN in Geneva, but they vanish almost instantly when they touch ordinary matter, releasing bursts of energy. That is why we do not see antimatter in our daily lives. It cannot survive in a world made of matter. When matter and antimatter meet, their mass turns into energy. Energy cannot be destroyed, only transformed. So, when an electron and a positron collide, they disappear as particles, but their energy reappears as light photons of gamma radiation, far more energetic than visible light. The universe, in a sense, keeps its books balanced. Mass is converted into energy, charge cancels out, and nothing is lost. Under different conditions, annihilations can also create showers of other short-lived particles before they decay into more stable forms. This perfect balance works on paper, but when we look at the universe itself, something doesn't quite add up. The Big Bang should have produced matter and antimatter in equal amounts. Each particle should have had a twin antiparticle. They should have met, annihilated, and left only radiation behind. Yet, we live in a universe made almost entirely of matter. Stars, planets, and people all exist because somehow there was a tiny excess, about one extra particle of matter for every billion that were destroyed. That small imbalance built everything we know. Physicists call this mystery baryon asymmetry. Why did matter win? Experiments have shown that the laws of physics are not perfectly symmetrical. Some particles decay just slightly differently than their antiparticles. This is known as CP violation, a subtle break in the expected balance between charge and parity. The difference is tiny but real, suggesting the universe has a built-in preference for matter. Still, the effect we can measure is not strong enough to explain the full imbalance, so the question remains open. On the smallest scales, matter and antimatter do cancel. Their charges and masses vanish in light. But on the largest scale, That perfect symmetry breaks. It is this tiny imperfection that allowed the universe to survive its own beginning. The idea of using antimatter has inspired both science and fiction. In theory, it is the most powerful energy source possible. When 1 gram of matter meets 1 gram of antimatter, the result releases about as much energy as a large nuclear explosion, tens of thousands of tons of TNT. This comes from Einstein's equation, E equals mc squared. Even a tiny amount of mass contains enormous energy. By comparison, burning gasoline releases only a few tens of kilojoules per gram, while matter-antimatter annihilation releases around 90 trillion joules. But there is a reason it remains theory. Antimatter is extremely hard to make and impossible to store in bulk. At CERN, scientists can create anti-hydrogen atoms and trap them briefly with magnetic fields, but only a few at a time. If even a speck touches normal matter, it annihilates instantly. Over the years, researchers have managed to hold antimatter for minutes, then hours, but the total amount is too small to see. If larger amounts ever touched ordinary material, the result would be violent. A chunk of antimatter meeting the walls of a container would release showers of high-energy gamma rays, deadly radiation that carries away the combined mass of both materials. Unlike chemical explosions that leave smoke or debris, annihilation leaves only energy. Antimatter isn't only made in labs. Nature produces it too. During thunderstorms, gamma rays can create positrons, which vanish almost immediately when they meet electrons. In space, extreme environments like the regions around black holes and neutron stars produce streams of antimatter. When these particles annihilate, they emit gamma rays that astronomers can detect. So, even though antimatter is rare, the universe still uses it as part of its natural energy flow. There is even a quiet connection to antimatter inside our own bodies. Some of the potassium in our tissues undergoes radioactive decay, creating a few positrons every second. These annihilate with electrons right away, producing tiny flashes of gamma rays. Medicine has found a way to use this process in PET scans, positron emission tomography. In these scans, doctors inject a substance that emits positrons, and when those positrons annihilate, detectors pick up the resulting gamma rays to build images of how organs work. In this sense, the meeting of matter and antimatter is not just a cosmic event. It happens inside hospitals and within our cells every day. Scientists have also wondered how antimatter interacts with gravity. If matter falls down, does antimatter fall up? For decades, it was an open question. In 2023, experiments at CERN's Alpha G project measured the motion of antihydrogen in Earth's gravity and found that it falls downward, just like ordinary matter. The precision of the measurement is still improving, but so far, there is no sign that antimatter behaves differently in this respect. That means their gravitational mass does not cancel, even if their charges do. And when they turn into light, that energy still responds to gravity. So the cancellation between matter and antimatter is never total. Locally, they vanish into energy, but globally, the leftover imbalance after the Big Bang means matter endured while antimatter faded away. That imbalance made the universe we live in. To picture it simply, think about a zebra. Its black and white stripes seem like opposites that might cancel out, yet together they create a pattern that helps it survive. The stripes confuse predators and deter biting flies, giving the zebra an advantage in the wild. In the same way, matter and antimatter are opposites whose meeting does not lead to emptiness. Their clash produces something new, energy, light, and sometimes even insight into how the universe keeps itself in balance. The zebra's pattern is not decoration, it is a function of survival. Likewise, the balance between matter and antimatter is what allows everything else to exist. Their interactions light up distant galaxies and power medical tools on Earth. What might look like destruction is, in truth, transformation. Their properties cancel, but energy remains. And from that energy, new matter can form again. The universe, it seems, never lets anything simply disappear. It turns opposites into motion, and from that motion, it keeps on building the world we know. When two black holes spiral together and merge, they release a rush of energy as gravitational waves. For a brief moment, that release can outshine the light from all the stars we can see, but not as flames or shock fronts. The power leaves as ripples in space-time itself. Those ripples travel for billions of years and arrive at Earth as faint stretches and squeezes. From these tiny changes, we can learn how heavy the black holes were, how fast they spun, and how far away the collision happened. Humanity first heard such a signal in 2015. Two giant instruments called LIGO, one in Washington State and one in Louisiana, picked up a clear chirp. Each facility has two 4-kilometer arms arranged in an L shape. Lasers bounce between mirrors at the ends, so even the smallest strain from a passing wave can be recorded. The data showed two black holes, each over 30 solar masses, circling faster and faster until they became one. In a blink, several suns' worth of energy turned into gravitational waves. Einstein predicted these waves a century earlier with general relativity. He modeled gravity as the curvature of space-time, not a force acting at a distance. He was unsure anyone could ever measure the effect, but the 2015 result proved that the faint signal is within reach. If we could see a passing wave, it would not look like light or smoke. It would look like a pattern that turns circles into ovals and back again, space stretching along one direction while squeezing along the other, then swapping in a steady rhythm. You can picture a ring of small objects floating in space. As the wave passes, the ring grows in one direction and shrinks in the other, then reverses. Nothing is pushed through space. Space itself changes shape. Many events can drive such waves, but two stand out: mergers of black holes and mergers of neutron stars. A neutron star is the collapsed core of a large star, so dense that a teaspoon would weigh billions of tons. When two neutron stars collide, they send out gravitational waves and also light across the spectrum: gamma rays, X-rays, radio, and a glow called a kilonova. That light reveals that heavy elements such as gold and platinum are forged in these crashes. In 2017, scientists observed both the waves and the light from the same neutron star merger, confirming long-standing ideas about the origin of many heavy elements. Listening for waves is like listening for long-distance animal calls. Whale songs can travel across ocean basins and carry information about identity and position. Elephants use very low rumbles that move through the ground far beyond our hearing. Gravitational waves are similar in spirit. They are signals that cross great distances, but they move through space-time and must be detected with extreme precision. Devices like LIGO and its European partner Virgo are tuned to those deep, quiet rumbles. Before 2015, most of our knowledge came from light: visible light from stars, radio from gas clouds, X-rays from hot disks, gamma rays from violent bursts. Each band reveals a different layer of the universe. Gravitational waves opened a new sense, They let us feel events that emit little or no light, like black hole mergers. With this sense, the universe is no longer only a picture, it has a soundtrack. If we could slow a wave and make it visible, standing in its path might feel like standing at the edge of a calm sea that becomes a moving floor. The ground would stretch and compress by amounts far smaller than an atom, yet in a precise pattern. The pattern is not noise. A black hole merger makes a short, rising chirp that cuts off after the final ringdown. A neutron star merger is longer and more layered, ending with flashes of light as the stars tear each other apart. The details encode mass, spin, distance, and the orientation of the orbits, like a fingerprint built into the wave shape. A drum offers another helpful image. Strike the drumhead, and it rings with tones that tell you about its size, tension, and where you hit it. After a merger, the new black hole rings in quasi-normal modes. Measuring those tones checks general relativity in strong gravity. Any mismatch could hint at new physics. The challenge is that the waves are tiny. The instruments must measure changes in length far smaller than a proton, while shielding against earthquakes, wind, trucks on nearby roads, and even the random motion of air molecules. Despite the difficulty, sensitivity keeps improving. Future ground-based projects, the Einstein Telescope in Europe and Cosmic Explorer in the United States, aim to hear fainter signals from farther away and from earlier times in cosmic history. Some scientists hope to catch hints from the very early universe. If space-time rippled during the rapid expansion after the Big Bang, those primordial waves could carry clues about how space-time itself formed. Detecting them would be like hearing the first heartbeat of the cosmos. Each kind of source has its own pattern. Black hole binaries make one family of signals. Neutron star binaries make another. A spinning, slightly lopsided neutron star might make a steady hum. The universe is like a forest we watched in silence for ages. Now we're starting to hear the calls and can match sounds to the unseen creatures that made them. Because the waves are invisible, scientists create visualizations to show what's happening. Two dense objects circle in tighter spirals. As they close in, ripples radiate outward with increasing strength and frequency until a brief, bright finale. The ripples then fade as they run across space, carrying the memory of the event. You can compare it to ripples from a splash in a pond. Even if you never saw the splash, the pattern reaching the shore tells you something. Hit the water at the center. Since the first detection, dozens of black hole mergers and several neutron star events have been logged. Each entry adds to a growing catalog, a map of how often these events happen, how heavy the objects are, and how they are distributed in the universe. In the next decade, a space mission called LISA will join the search. 3 spacecraft, flying in a triangle millions of kilometers wide, will measure lower frequency waves than ground-based detectors can hear. Those waves come from supermassive black hole mergers and other slow, massive systems. With LISA, we will listen to a different part of the cosmic band. We are also learning to hear the background. Networks of radio telescopes monitor the regular ticks of spinning neutron stars called pulsars. Tiny timing shifts caused by long wavelength waves can reveal a faint hum produced by many distant sources at once. Adding this method to ground and space detectors gives us a fuller picture, like adding new instruments to an orchestra. It helps to remember that waves carry energy and information. They move at the speed of light, the fastest anything can go. When a distant merger happens, light and gravitational waves leave together. For some events that produce both, they arrive together as well, allowing tests of how waves travel and how gravity works across vast distances. So far, the speed agrees with relativity. One value of this new field is the chance to test ideas in places no lab can reach. The ring down checks relativity where gravity is strongest. Neutron star mergers probe matter at extreme density and temperature. Any small and repeated deviation in the wave shapes could point to new physics, modified gravity, unexpected behavior at the horizon, or hints of quantum structure in spacetime. Claims of echoes after ring downs have been explored and debated. The community continues to refine methods to separate real features from noise. The practical gains are less obvious, but still real. Techniques developed to isolate tiny signals from large backgrounds feed into other areas. Laser stabilization, vibration control, novel data analysis. As with earlier revolutions, quantum mechanics enabling electronics, relativity enabling GPS discovery often brings tools we cannot yet predict. If you want one more everyday picture, think about tides. The moon and the sun raise the oceans in slow cycles. Gravitational waves are like tides for space-time itself. They wash across every object, atoms, mountains, clouds, with effects so small that life continues without noticing. Our instruments notice. Each passing wave is a record. Who collided, how heavy they were, how fast they danced, and when it happened. Standing on an open plain, you might feel a distant stampede through the ground before you could see dust on the horizon. The merging of two black holes is that stampede on a cosmic scale. The ground, in this case, is space-time. The signal is quiet but precise. In its rise, peak, and fade are the stories of dark objects we cannot see with light. What was once a silent film of the universe now has sound. With better ears on Earth and in space, that sound will grow richer, revealing how black holes form and grow, how elements are made, and how the first structures took shape. And always carried on those waves is the shared limit of the universe's speed. Gravitational waves, like light, race across the dark at the speed of light, arriving as faithful messengers from events that ended long ago.